Question 4 from Paper 2 of the 2024 Higher Physics Examination from the SQA. On the 26th of September 2022, Double Asteroid Redirection Test, DART for short, collided with Dimorphos, a small asteroid that is in orbit around the larger asteroid Didymos. You can see that in the diagram. The aim of the mission was to test a defence system that could be used to redirect an asteroid that is on collision course with Earth. Now, when DART collided with Dimorphos, the kinetic energy of DART was transferred to Dimorphos, and this caused Dimorphos to change its path. Very interesting mission there. You can look that up on the internet, it's fascinating. Part A says the mass of Didymos is taken to be 5.3 times 10 to the power 11 kilograms, and the mass of the Earth is 6.0 times 10 to the power 24 kilograms. And for 2 marks, we're asked to compare the mass of the Earth with the mass of Didymos in terms of orders of magnitude. Well, we start off by comparing it as a ratio, the mass of the Earth divided by the mass of Didymos. And we put in our numbers. The mass of the Earth is going to be 6.0 and times 10 to the power 24 kilograms. The mass of Didymos, we divide by that, is going to be 5.3 times 10 to the power 11 kilograms. Now we're just comparing things, so the 2 kilograms will cancel out. Now we're comparing orders of magnitude. We look at these two front numbers first, and 6 divided by 5 is roughly equal to 1. So as an estimate, we can just say 1. Now the powers are the orders of magnitude in reality, so it's 1 times 10 to the power, and we've got a power of 24 divided by a power of 11. We take 11 from 24. That's the rules of powers as you found out in your maths class. So we're going to have 24 take away 11 is going to leave us with 13. So there we can see that the ratio of the mass of the Earth divided by the mass of Didymos is going to be 1 times 10 to the power 13, and it's this number here, the 13 number, which gives us the orders of magnitude. So our final statement would be then that the mass of Earth compared with the mass of Didymos is 13 orders of magnitude bigger. Question 4, Part A continued. When DART collided with Dimorphos, the distance between Earth and Didymos was 1.1 times 10 to the power 10 metres. And for 3 marks, we're asked to determine the gravitational force between the Earth and Didymos. Well, we know the gravitational force between two objects. This will be M1, and that's going to be M2. And this is going to be the distance between the centres, which we'll call R. We know there's a gravitational force F, and it's going to equal to the universal gravitational constant G times M1 times M2, all divided by the distance between the centres squared. That's how we calculate the gravitational force between those two masses. So we have got the mass of the Earth and the mass of Didymos. We know that the mass of the Earth is 6 times 10 to the power 24. We know the mass of Didymos is going to be 5.3 times 10 to the power 11. So we can put in our numbers now. So the force of gravitational attraction is G. The universal gravitational constant is 6.67 times 10 to the minus 11. I'll leave out the units for the moment. Times the mass of, say, M1, which we'll call the mass of the Earth, which is 6 times 10 to the power 24. And then multiplied by the mass of Didymos, which is going to be 5.3 times 10 to the power 11. And we'll put a bracket around that like that. Divided by the radius squared, the distance between the two centres, and that's going to be 1.1 times 10 to the power 10, and we have to square that. And our force is going to be measured in units, and the gravitational force, we do that in your calculator, is 1.75 times 10 to the power 6 newtons. Question 4b. DART had a mass of 570 kilograms and was travelling at 6.6 kilometres per second when it collided head-on with Dimorphos. And for 3 marks, we have to calculate the maximum kinetic energy transferred from DART to Dimorphos during the collision. Well, we know our kinetic energy formula, EK, is going to equal to 1/2 times the mass times the speed squared. And we know the mass of DART, and that's going to be equal to 570 kilograms. We don't have to change anything there. We know the speed which the DART was approaching, and that was going to be 6.6 kilometres per second. Now we can't use kilometers per second, we have to change it into meters per second, so we just simply multiply that by 1,000, and the quick way to do it is go 6.6 times 10 to the power 3 meters per second. So plug these into your formula. EK is going to equal to 1/2 times the mass, 570, times, and it's going to be 6.6, put in brackets 6.6 times 10 to the power 3 all squared. Now we do that in our calculators, we end up with a value of 1.24 times 10 to the power 10, and units for kinetic energy is joules. So that's the maximum kinetic energy that could be transferred to Dimorphos. Question 4b continued part 2. Complete the sketch graph of force F against T for the force exerted on Dimorphos by Dart during the collision. Numerical values are not required for this axis, and of course it gives you instructions. You can find another graph later on. Now when something collides into something, the force is going to be actually spread out, and the best way to describe it is this picture here. The force starts off at 0 just before the collision, and because it's colliding into a very, very dense, hard asteroid, then you're going to have a kind of steep rise of force, and it's going to occur over a very short time like that. So that's the sort of graph you're going to get for the force against time. So we see we're going to have a peak force occurring, and the force builds up, and it was over a certain time it took for the collision to take place. So that's the graph you'd expect for the collision of Dart on the asteroid Dimorphos if we look at the force time graph.